Alright everyone, so this is the 27th lecture in our series on algebraic number theory. Today we're just going to talk about a class of rings called discrete valuation rings. So I'll give you a little bit of motivation for today's lecture. So last time we saw that we saw the localizations of Dedekind domains. Are again Dedekind domains. Okay. So in the previous lecture we proved that being a Dedekind domain is basically a local property. I should say of Dedekind domains. Okay. So it turns out basically that in order to prove unique factorization of ideals, we're going to study these local Dedekind domains a little more closely. Study Dedekind domains more closely. And it turns out, so there's a class of rings called discrete valuation rings. It turns out the local Dedekind domains are going to be what's called a discrete valuation ring. Turns out local Dedekind domains are what are called discrete valuation rings. So I haven't told you what that is. That's the point of this lecture. And we're not going to prove that local Dedekind domains are discrete valuations in this lecture because it would the proof is a little bit long and I've already got a lot of things to prove in this lecture. But in the next lecture we'll prove that local Dedekind domains are discrete valuation rings. In this lecture we're going to just focus on what the idea of a discrete valuation ring. Okay, so the overview of this lecture, we're going to define discrete valuations, and discrete valuation rings. These are DVRs for short. We're going to classify ideals in DVRs. So it turns out every ideal in a DVR has a special form. And then we're going to prove a characterization of DVRs. So there's going to be an initial definition of DVRs that has to do with this concept of a discrete valuation, as the name would suggest. But there's a kind of easier classification, possibly more useful. We'll prove that R is a DVR if and only if R is a principal ideal domain with a unique non-zero prime ideal. And this is going to be, this third thing is going to be the main tool that helps us prove that local Dedekind domains are discrete valuation rings. Okay. So let's go ahead and get started. I'm going to tell you what a discrete valuation is first. So definition, this is 27.1. We're going to let K be a field, just any field. A discrete valuation on K, I should do this in red. A discrete valuation this is going to be a function. It's a homomorphism. Nu from collection of non-zero elements of K to Z, which satisfies mainly one property, such that nu of A plus B is at least the minimum of nu of A and nu of B. Okay. So, discrete valuation is a homomorphism from K cross to Z. Typically, we extend this nu to so K cross is the non-zero elements. To extend it to K, I just have to tell you where 0 goes. Extend nu to K by defining nu of 0 to be infinity. So there's, you might say, okay, but infinity is not a number. Just pretend it's the symbol infinity and it satisfies the property that it's greater than or equal to every integer. So it's not gonna, you won't run into any contradictions there. Okay, so this is the definition. I should give you an example just so that you have something to think about. Here's the quintessential example of a discrete valuation. We're going to let K equal Q, and we're going to let P and Z be a prime. Then for A over B and Q, with, let's say A is not equal to 0, we define nu sub P of A over B. This is going to be order, so how many times P divides A minus how many times P divides B. Okay. It turns out that this nu sub P defines a discrete valuation. And this P is a discrete valuation. On to Q. Okay. So you can check if I have, basically, the way you can think about this inequality holding is if I know P divides A to some power and P divides B to some power, then P has to divide A plus B to at least that power. So that's how you get this inequality condition. And it's a homomorphism because when I take the product of two fractions, the number of p's that appears in the numerator minus the number of p's that appears in the denominator is multiplicative. Okay, so you can check this on your own if you're skeptical that this actually satisfies 27.1. Okay. So this is what a discrete valuation is. What is a discrete valuation ring? So 27.3 definition. If nu is a discrete valuation, on a field K, we define the associated valuation ring This is going to be A, which is a set of x and k, such that nu of x is positive, or non-negative, I guess I should say. So you can check, I guess, what do I want to say? If R is an integral domain and is the valuation ring of frac R for some valuation nu on frac R, then we say A or R is a discrete valuation ring. Okay. So I would say it's not immediately obvious from the definition why this thing even is a ring, but you can check using the homomorphism property and this inequality that this actually does satisfy it's closed under addition and multiplication, basically, and it contains 1 and 0. Okay, so this is what I mean when I say discrete valuation ring. It's the valuation ring of some, they should say valuation ring, of some valuation on the fraction field. Okay. And I should also say discrete here because there is a concept of a more general valuation, and it is a little different. So, okay. So, the next thing I'm going to do, it turns out the ideals in this ring have a very special form. Okay. That's going to be this. Oh, maybe I should mention what it looks like in our previous example. So, example, the valuation ring of, let's say, Q with the valuation v sub p is something called Z. I want to say Z localized to P. These are all the fractions, all the rational numbers, such that, so I need the valuation of this thing to be positive, which basically just means that P doesn't divide the denominator, or, yeah, I guess like this, with P not divided B, I'll just say when A over B is in lowest terms. So this is a ring, and this is the discrete valuation ring of Q with respect to the valuation nu sub p. Okay, so what I want to do now is classify ideals in discrete valuation rings. Okay. So here's the proposition. We're going to let A be a discrete valuation ring. I'm just going to say DVR. Then A has a unique prime ideal. A has a unique prime ideal, and I can say something more. Furthermore, this ideal is principal and every non-zero ideal has the form p to the k for k greater than or equal to 0. Here p is this unique non-zero parameter, or unique non-zero. Okay, so basically DVR has this principal prime ideal, and every other ideal is just a power of that. Okay. So we're going to prove this. We're going to prove it in a few steps. So we follow the steps below. Okay, so step 1, we're going to show that the units in A are exactly the set of x in A such that nu, so here's nu is the discrete valuation associated to A. It's a valuation on the fraction field of A. Okay, and my claim is that the units in A are exactly the elements of valuation 0, 2, every element of, what do I want to say here? Sorry. So we're going to choose an element of minimal non-zero valuation. Okay, once I have an element minimal non-zero valuation, let's say pi, then we're going to show every element of A is a unit times pi to the k for k at least 0. And finally, we're going to show that every ideal has the form pi to the k for k greater than or equal to every non-zero ideal. And from these 3 steps, we'll be able to prove the result. Okay, so let's consider step 1. We're going to first show A cross is contained here. We're going to let A be an A cross. Then 1 over A is also an A. Hence, what can we say here? Well, A is the things of valuation at least 0. So I know that the valuation of A and the valuation of 1 over A, these are both greater than or equal to 0. However, the valuation of A times 1 over A, this is the valuation of 1, which is just 0. So you can check using the fact that the valuation of 1 is the valuation of 1 times the valuation of 1. Yeah, maybe you need to know something like... Oh, no, sorry, yeah. The valuation of 1 is the valuation of 1 plus the valuation of 1, which forces this to be 0. But this is a homomorphism, so this is v of A plus, I should say nu. This thing, if these are both positive or non-negative and they sum to 0, then they both have to actually be 0. Okay, so this proves one containment. A cross is contained in the set of X and A, such that okay. Now we're going to suppose that the other direction is similarly easy. If nu of A equals 0, well, you can basically use the same equation to show that nu of 1 over A also equals 0. So 1 over A is also an A, because A again is the set of things at least 0. Thus, A is in A cross. Okay, so there's step 1. The units are exactly the things of valuation 0. Okay, step 2. First, we're going to show we can find such a pi. So this follows from the well-ordering principle. So first note that a set of v of x such that x is not in A kick out A cross. Yeah, so maybe we also need an assumption that A is not a field. I guess if A is a field, yeah, if A is a field, then A probably is a DVR with respect to like the trivial valuation. So I guess we should also assume I think maybe that's even a part of the definition in the definition of DVR. I'm not sure, but it's mostly a triviality for us. Okay, so we're going to need this assumption down here to get that this subset of the natural numbers is non-empty. And thus has a minimal element. By well ordering. We're going to choose this. We're going to let A, or pi, be such that nu of pi is minimal. pi non-zero non-unit. Okay. Okay, so we're going to choose A and A. By the division algorithm, we can write nu of A is n times nu of pi plus r, where 0 is less than or equal to r is less than nu of pi. Note that nu of A over pi to the n now. So n times nu of A, I can bring this inside because it's a homomorphism, and then I can divide over, or I guess subtract, and then it'll give me a division in the ring A. So this is just using the homomorphism property. Nu of this guy equals r. Which is strictly less than nu of pi. Okay, so in particular, this means that r has to be 0. R equals 0, and a over pi to the n, well, this is a unit in A. Okay. So this proves step 2. So this r equals 0 is by the minimality of nu of pi. Because this thing, this is an element of A, because we know that this r is at least 0. So this is an element, A over pi to the n is an element of A. And since nu has minimal non-zero valuation, and this has valuation less than the valuation of pi, it has to be 0. Okay, so we'll do step 3 now. So we're going to let I subset of A be an ideal. Now, I guess it should be a non-zero ideal. If A equals 0 and A is an I, then A is going to be U times pi to the k for k equals 0. And, I should mention here that n is necessarily a non-negative integer because these are both elements of the natural numbers. Okay. A is going to be a unit times pi to the k for k equals 0. And then, so I necessarily contains some power of k. So we can choose a minimal power of k that I contains. Choose. K, so that pi to the k is an I, and k is the minimal. Such not negative integer. Okay. So the claim is going to be that I is equal to pi to the k. So, what do I want to say? Clearly, you know, the ideal generated by pi to the k is contained in I. If I've got some other guy, u times pi to the k prime in I, remember every element looks like that has this form, then, well, well, by hypothesis k is greater than or equal to k prime, so what does this mean? This means that u times pi to the k prime minus k. This is an element of A. You can check the valuation here. It's going to be k prime minus, or it's going to be the valuation of nu times k prime minus k, which is at least 0. So u times pi to the k prime. This is u times pi to the k prime minus k times pi to the k, which is in the ideal generated by pi to the k. So we took an arbitrary element of I, and we showed that it was necessarily in this ideal. Thus, I is equal to the ideal generated by pi to the k. Okay, how do we finish the proof? First, observe that the ideal generated by pi is necessarily prime. Okay, how do you know that this ideal is prime? Well, everything outside of this ideal basically is a unit, because this thing has minimal valuation. If I have something that's outside of this ring, since A kick out pi equals A cross, and the product of two units is a unit. Okay. So what else do I want to say? I guess also I should mention pi is not a unit because it has non-zero valuation. Okay, so I've got my principal prime. To see that this is the only prime, just notice that all these ideals from step 3 are not prime. For k at least 2, this ideal is not prime because pi times pi is in it, or pi times pi times pi is in it, but pi is not in it. Yeah, if pi to the k, if pi were in any of these ideals, then this would be then it would force pi to be a unit, basically. What do I want to say? It's not prime. This ideal is not prime. So the ideal generated by pi is the only prime. Prime ideal. By step 3. And every ideal is a power of by 3 as well. Okay. So this proves the classification of ideals in a discrete valuation ring. So what do I want to say here? You might be a little concerned. I never use the inequality property at all or at least it didn't feel like I did. Where it comes up is basically in the very definition of this ring A. So to show A as a ring, you have to use this inequality property. So all this stuff is not going to like even make sense if you don't have that inequality property for your valuation. Okay, so this finishes the proof of the I want to say 27.5, the proposition. Okay, and then we'll have 27.6. This is the last thing in this lecture as a corollary of this result. Okay, and the proposition and integral domain I should say, which is not a field. Is a DVR if and only if it is a PID with a unique prime ideal. So we've basically proven one direction of this implication already with the classification of ideals above. So proof the implication DVR implies PID plus unique prime ideal follows immediately from 27.5. So we need to work to get the other direction. Okay. However, this one's also not too bad. We're going to suppose A is a PID with a unique non-zero prime ideal. I always forget this non-zero condition. Suppose A is a PID with a unique non-zero prime ideal. Okay, we're going to choose a generator for this ideal, this non-zero prime, pi for the unique prime ideal. Okay, so this is a PID. It's going to be generated by a single element. What do I want to say? Okay, so the thing to notice here is that every irreducible, okay, so since A is a PID, it's also a UFD. Since it's UFD, irreducible elements are the same thing as prime elements. So these every irreducible generates a prime ideal. And since there's only one of these, they all generate the same ideal, which forces them to all be a unit times this pi. This has as a consequence, well, every element of A factors as a product of irreducibles because it's a UFD. What does this mean? Every element of A has a certain form. It's this form from above in step 2. U times pi to the k for some k greater than or equal to 0. Okay, and here U is a unit again. Now we can define evaluation. Well, maybe I should add another sentence here. So if this is what A looks like, then the fraction field of A, every element there has a similar form. Every element of frac A has the form U times pi to the k, with U as a unit in A, and k is now not necessarily greater than or equal to 0, but just an integer. Okay, and then we can define evaluation here. Evaluation from frac A cross to Z, every non-zero, I'll just write across here, which sends U times pi to the k to k. And then with this, so you can check this is evaluation and that A is the associated valuation. Right. Okay. So we introduced the concept of a DVR. We classified ideals in a DVR. And then we gave an alternate characterization of what a DVR is. In the next lecture, we'll prove that a DVR is actually the same thing as a local Dedekind domain. And then we'll use all these properties to prove unique factorization in Dedekind domains. Unique factorization of ideals should be more specific. Okay. So we'll see you in the next lecture.